Chapter 8, Open Stack Physics, Momentum and Collisions. And, I just want to point out that I am giving a chapter summary of a book that I didn't write. I would do things differently. I would introduce momentum way at the beginning. Let's just get into it. Okay, so momentum, we define momentum as P is mv. It's the product of an object's mass and its velocity. Right, so imagine this is moving, has a mass, has a velocity. Now, velocity is a vector, so momentum is a vector because mass is a scalar. What are the units for momentum? Well, kilograms, meters per second. So this is kilograms, meters per second. That's the only unit. There's no shortcut for that, so that's fine. Now, let's just jump into what's called the momentum principle. It's a big deal, right? And in fact, there are three big deals in this semester. Principle, not POW. Okay, so the momentum principle says this. It says that the net force on an object, F net, is the change in momentum with respect to time. That's the momentum principle. Okay. So if I apply a net force, it's going to change the momentum. And really it goes back to that fundamental nature of forces. We talk about forces changing the motion of an object, and we can say, okay, it changes the velocity. It makes it have an acceleration. You can also say it changes the momentum. It's a different way of saying it. It's a different way of encapsulating the problem. And maybe a better way. Okay. But in fact, it's the same as this. For the most part, it's the same as that. So if I use the momentum is mass times velocity, and I put that in over here, this is going to be the change in mass and velocity with respect to time. Now, there's a very, very, very good chance that the mass does not change. If the mass of the object does not change, I can pull that out of there, and I get, let's just erase this, because I was poor in my space management, mass times delta V delta T. I can only do that if the mass is constant. Okay. But now what's delta V delta T? What's the rate of change of velocity? You know the answer. You do. It's acceleration. I've still got the M there. So the momentum principle is essentially the same as Newton's second law. It says that forces change the motion of an object. It's just a different way of looking at that in terms of momentum. Now, why? Why would we do that? Well, it helps us do a few things. But I want to write the momentum principle. Oh, and I said there were three big ideas in the semester, and those big ideas, now we have two of them. And you could say the Newton's second law is the same thing, and I respect you for saying that. Okay, but we have the momentum principle. That's one big idea. And then we have the work energy principle. Those are two very, very, very big ideas. I guess the only other big idea would be to say, how do we define these things like velocity and acceleration and position? But other than that, this is what we've done. Now, yeah, there have been some forces that we had. We had the gravitational force, real gravity, we had springs, we had contact forces, we had, types of energy, but those are the big ideas, and this is what's so great about physics, right, is that we have these very powerful ideas that can be used in many, many different ways. So you could say I have two equations that describe pretty much everything we've done, and that is true. Okay. But let me show you something really important, because I'm going to rewrite this equation. I'm going to multiply both sides by delta t. I get delta p, the change momentum, is F net. I'm just going to write that as in delta t. That's important, and we're going to get into this. It's called the momentum. It's called impulse, but it's not super important. Remember how we defined work. Work was F delta R cosine theta. And I'm going to write the work energy principle as the work F. Let's just write that as F delta R cosine theta is delta E, the change in energy. This is the work energy principle. This is the momentum principle. Now, there are some very, very, very important similarities and some very important differences. Number one, you'll notice that I cut that off. Vector, vector. Scalar, 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 scalar. So the work energy principle is a scalar relationship. It does not give us direction. The momentum principle is a vector relationship. It gives us direction and vector values. Number 2, look at that. A force and a time. A force and a displacement. Don't worry about the cosine theta because usually it's 1. But this is where, if we think about a force applied over a distance, we get a change in energy. A force applied over some time interval gives us a change in momentum. And yes, momentum and kinetic energy both depend on mass and velocity. So P is mv, and for the most part, kinetic energy is the energy, 1/2 mv squared. So there's they both describe mass, velocity, forces, but this one deals with change of position, this one deals with time. This one's a scalar, that one's a vector. I think it's important to think about that when you're thinking about problems. But in general, if we're dealing with a change in time, momentum principle. If we're dealing with a change in position, work energy. Not always, in general. Okay. So they did say they called this impulse. And this is one thing that I remember like, what? I don't get it. So which side is impulse? Well, they're both impulse. The change in momentum is the impulse, but normally we say the force times the time interval is impulse. And it's not super important. It's important to realize that's just the momentum principle. Now, I do want to show a sketch because they talk about it in the book about force versus time graphs. And let's just do 2 things. Let's do a force versus time and a force versus position, and not the same interaction because I don't want to make them match up. So here's force versus time, and they give something like this. So say something collides and it has a force as a function of time like that. If I find the area under this curve, it's equal, no, I didn't spell it right. It's equal to the change in momentum. But notice I didn't put a vector over that, right? Because you can only make a force versus time graph in 1 dimension, because if force is a vector, you'd have to make an x graph, a y graph, and a z graph. And so this is just one of those dimensions. They don't really explicitly say that. But the area under that would be F delta t, which is the change in momentum. Now remember, if we have F as a function of position, then the area under this is the change in energy. And both of those you can have negative areas if it goes below the axis. But again, these are in 1 dimension, so it's kind of hard to do in multi-dimensions. It's sometimes useful. Let's look at the most coolest thing that we want to talk about, and that's collisions. Turns out to be very important in physics. Okay, so imagine that I have these 2 objects, and they're moving, and they collide, and then stuff happens. How do we describe that interaction? It's not trivial, because that interaction force is not easily characterized, right? How do I describe the force this exerts on this, or the force this exerts on that? It's not easy to do. Okay, but we're going to do it anyway. So let's imagine that we have 2 objects. I have object A and object B. And object A is moving this way with I'm just going to go ahead and say it has a momentum PA1, and this has a momentum PB1. So they both have mass, they have velocity, and they're moving, and they're going to collide, and at some point they are interacting. Well, in this case, if they're interacting, then B is going to push on A. So I'm going to draw that this way. I'm going to say F, B on A. But if you remember Newton's 3rd law, forces come in pairs. So if B pushes on A pushes on B with an equal and opposite magnitude. So F, A on B. And those are vectors. Okay, they are vectors. And since it's a collision, FB on A is equal to negative FA on B. That's Newton's 3rd law. And then after the collision, I shouldn't have put that there. after the collision, let's say A is doing this, P, A, 2, and B is doing this. They maybe even stick together. It doesn't matter. It doesn't matter what they do. It's doing something. P, B, 2. And also this takes some time, dt. The collision doesn't last forever. It takes some time interval. Okay. So before the collision, during the collision, after the collision. Well, if you just look at object A, it has a momentum, then it has a force for some time, and then it has a new momentum. So it has a change in momentum, and we can write the momentum principle as the following. I'll write it out the long way. FB on A, that's the only force acting on it in this case, is equal to delta PA delta T. I can solve that for, no, let's just leave it. And then I can do the same thing for B, because it goes before the collision, during the collision there's a force, and then after the collision. So FA on B is the change in momentum of B with respect to time. But check this out. This force is the opposite of that force. So I could say negative FBA is equal to delta PB delta T, right? I just replaced FAB with negative FBA. Now I'm going to multiply both sides by negative, so this becomes positive and that becomes negative. Now, boom, boom. These two are the same, so these two have to be the same. So I can say delta PA delta T is negative delta PB delta T. Now, one last thing to make this super awesome. It's impossible for the time interval for the interaction of A to be different than the time interval for the interaction for B. They're the same. It's the same time interval. So these delta T's are the same, so they cancel. And I'm going to add this to the other side. I get delta PA plus delta PB equals 0. This says the change momentum of the balls added together is 0. Or the change in momentum, the momentum doesn't change because it's 0. The change in momentum has to be 0. Or we could say the momentum is constant. That's one way of looking at it. So in this collision, I can say the momentum before is equal to the momentum afterwards. That's what this says. Okay. So let's write that out. I can write that as the following equation. PA1 vector plus PB1 vector equals PB2 vector plus, I don't know why I did B that out of order. I was just thinking. So this is what we have for a collision. This is conservation of momentum. Conservation. I'm going to say of P because I don't want to write out momentum. Because you have trouble spelling things when you're working on the board. I don't know how anyone does spelling bees because of all that pressure. Now, what assumptions do we make to come up with conservation of momentum? Because that tells us when momentum is not conserved. So the key here was that the only force acting on A was due to B, and the only force acting on B was due to A. If that's true, then momentum is conserved. Now, just imagine, let's break it. What would have to happen to break this? Well, imagine that like A has a rocket engine on it. So there's an extra force. So if momentum's going to change because of the rocket force plus the collision plus the rocket force. So now I can't set those two changes in momentum equal and opposite to each other. So momentum would not be conserved. In general, I'm going to remove that. In general, we like to look at the system. Again, we're back to that system. The system of the objects. And if there's no external forces on the system of objects, then we'd say momentum is conserved. So if I choose the system of ball A and ball B, no external forces, momentum's conserved. And we can even cheat, right? Because imagine now that I take these two, and I throw them in the air. I'm not going to do it because I'm going to get chalk dust all over the place. I throw them in the air and they collide. I still got chalk dust everywhere. Well, there's an external force on the system of the ball plus the eraser. The gravitational force is pulling them down. So momentum is not conserved. However, we can cheat because if the collision takes place over a super short time interval, which it does, then I can say the momentum right before the collision and the momentum right after the collision has to be the same because the gravitational force has very little time to change the momentum of the system. So we can do that, right? We can do very, very short time interval collisions and kind of ignore those external forces. And we do that sometimes. But okay, so that's your collisions. It's pretty awesome. Vectors. And we'll do... we'll start off with a one-dimensional collision because they're easier, and then I'll talk about two. But it can get pretty bad pretty quick. Yeah, and the book starts off with elastic collisions, but I'm going to start off with the simplest collision ever, an inelastic collision. Let's consider an inelastic collision. Okay, so imagine I have, and it doesn't really matter, A with some momentum PA1, B with momentum PB1, and they collide. And then in this collision is special because after the collision, they stick together. So they stick together, that means that they have the same velocity. I'll call it V2. And that's an inelastic collision. In an inelastic collision, the objects have the same velocity at the end because they're stuck together. So we can still say momentum's conserved. I can say, I'm going to write this out as a vector, okay, and then we'll do it in a one-dimensional case. As a vector, I'm going to write this as MAVA1 vector plus MBVB1 vector. Right, that's the initial momentum. It's going to equal the final momentum, which will be MA plus MB V2. Because they have the same velocity, I can factor out that velocity term. And that's it. That's my inelastic collision equation. You know, what will happen is you may not know one of the velocities and you have to solve for it, and that's fine. In one dimension, it's pretty easy. These just become x components of velocity, and I'm not even going to rewrite it because there's no point. We'll do some problems about collisions, but I'm just doing a chapter summary. I'm not doing everything, just chapter summary. Okay. Now there's another extreme version of a collision. But you'll notice inelastic collisions conserve momentum as long as the external force is 0 or negligible. Now suppose that they don't stick together. And this is where it gets complicated. So PA2, PB2. So they don't stick together. They collide and they don't stick together. So again, I have conservation momentum. And I'm going to write it as in terms of velocities. MAVA1 plus MBVB1 equals MAVA2 plus MBVB2. And I want to point out that as a vector equation, there's just one, but in two dimensions, this is actually two equations, right? This is VAX1, VBX1, VAX2, VBX2. So it's two equations because you have the same thing for the y equation too. There's a special kind of collision called elastic collisions, where not only is the total momentum conserved, the momentum before and after is conserved, but also K1 is equal to K2. The kinetic energy is conserved. The kinetic energy is conserved. So 1/2 MAVA1 squared plus 1/2 MBVB1 squared equals 1/2 MAVA2 squared plus 1/2 MBVB2 squared. And you'll notice that there's no vectors over there because kinetic energy is a scalar quantity. That's the magnitude of the velocity. So you can imagine this is three equations, right? 2 for momentum in the x and y directions, 1 here. But now when we square these things get a little, they can get a little complicated. It's not too bad in one dimension, but it is pretty bad. I want to go back to the inelastic collision. So imagine I have an object that this is moving and it collides and then they stick together. So kinetic energy is not conserved. The kinetic energy here would be more than right there. But energy is conserved. So where did the energy go, right? If I have a closed system and there's no work done on the system, then the energy had to go somewhere. And it's hard to quantify exactly where it is, but imagine 2 objects colliding together. Well, they will increase in temperature. They will change. They'll get deformed. They will produce sound. All of those things are changes in energy that are where that lost kinetic energy goes to. So energy is still conserved. It's just kinetic energy is not conserved. But for both an elastic and an inelastic collision with no external forces, momentum is conserved. Okay. Now, they do have a thing in this chapter about rockets and the rocket equation, which is kind of cool, but it's not derived, and you can't derive it without doing some serious differential equations. So I'm just going to. But in general, a rocket works by taking mass and throwing it. Okay. If you throw mass, then if you have a rocket with propellant, and you throw mass that way, then that has momentum this way. In order to conserve momentum, the rocket has to have momentum the other way. And you keep throwing things out. So imagine being on a cart and you keep throwing stuff, right? You'll get pushed this way. And that's how a rocket works. It doesn't need air. A plane works by throwing air back, but it takes the air in front of it and throws it back. A rocket doesn't need air, so it brings its own fuel and its own air to throw. Okay. And you can derive, it's a great example of non-constant mass, because as a rocket uses its mass and shoots it out, it decreases in its own mass. So, and that's why some of these rockets are so large. They're mostly fuel, because you have to increase the mass of the fuel before you throw the fuel. So you have to bring all the fuel with you. So, but I'm not going to go into that. It's a cool problem, and I will show you some cool momentum stuff. But that's that. So I like to show you the equations at the end. The most important equations, there's not that many. Momentum, mass times velocity. The momentum principle, F net, delta P, delta T. And the impulse equation is the same thing. Delta P is F net, delta T. It's the same equation set. Other than that, there's no other new equations. It's a new way of thinking about things. Chapter 8.